Hi everyone, my name is Ruzica Piskac and lots of greetings from New Haven. I'm really sorry that I'm not sitting with you in a beautiful Australia, but instead I'm in my office. So I hope that next time we meet, it will be in person. So thank you very much for inviting me. And this talk today will be about verification of configuration files. When it comes to configuration files, the title, although a bit long, captures actually the essence. We first need to synthesize the specification for configuration files so that we could actually verify them. And to tell you how I became interested in this topic is I need to tell you more about a very smart postdoc that they had, Enan Jai, and a couple of years back, Enan approached me and asked me, so you do all this work on the verification on the program separation logic using automated reasoning, but why you don't address programs that really matter? So I asked him, what are those programs? And he says, like, how about configuration files? And Enan also approached me with the data, which is a survey that was done almost 10 years back, which showed that a real problem for big systems and why are they down is actually lying in a wrongly setting configuration files. And if you look, my standard job of hunting bugs in the code, that is only source of the 15% of the downtime. Majority, 31%, almost 1/3, was because there were some errors in configuration files. So when it comes to configuration files, you might actually ask yourself, like, how do we even verify them and what's there to verify? Because if we are honest, they look something like this, right? You have a bunch of code that doesn't follow any traditional program as structures or that you have usually seen the program. That's the code that was written probably a couple of years back, if not a decade back. And what we will do, you will probably change only a couple of lines that you need to configure your system. So if you look at this code here and you run it, with Apache and MySQL, it's for configuration files for Apache and MySQL. And what happens is segmentation fault. And if I tell you, oh, you just changed the things which are here in the given square, and you look at that square, you can see that there is nothing fishy, you're just loading libraries. But if you would check by more thorough analysis, you will see that the problem lies in the fact that you are loading one library before the other. Now you might get puzzled, like, is this really an error? Yes, it is. This is actually what was causing the system would crash. And not only that, it would actually it wouldn't actually work properly. So what we have a tool called config-C, and we have config-B and a couple of other tools, where when you run this tool on this file itself, you don't even need to isolate parts that you changed. What will happen then, our tool will tell you, look, I think that you have loaded this library before the other one. Excuse me. Now let's go to the next example. Again, same problem. This one we try to install SQL, and there is only one line that you change, which was this thing here. You're setting general log. This is your own personal file. You want to put it in the var log myself, blah, blah. So what is happening here is you might think, like, what is the problem is that maybe file does not exist. Maybe you don't permission rights, but file does exist, and you can write in the file, and nevertheless, the program simply fails to start. So what our tool tell you, it will tell you the following. The main problem is that general log is not really general log. It's a Boolean which actually tells that you will be using general log. And if you want to set up general log file, you will use this general log file, and then you provide the file that you have seen above. So again, running our tool on this example will whole example will tell you, look, I expected here an integer with very strong probability 1.0, which is like, I really think that integer should be, and that should come here on the for the variable general log. Now, if you think about, clearly configuration files could be problematic. I mean, we have just seen very simple examples, and we were actually lucky in both these examples, because what was happening was we had configuration files, we changed something, things would crash, things didn't work. Then we would check out of the user forum like Stack Overflow or somewhere else, and then we would learn what was the problem. We would change these problems, and everything would be great because things would then work, and we fixed our configuration files. So you can see errors are actually there are no really errors that like error messages that will tell you this is what is the problem. You need to describe what has happened, but there are also very sneaky errors which are actually don't result in the crashes. They're actually just causing that the program suddenly starts to behave weirdly, and you cannot see why is this the case. So first problem is, right, how do you even characterize that something is an error? Okay, if it crashes, it is an error, but what when things are actually just not working properly? Second problem is like maybe we don't even have specifications, so we cannot apply standard techniques that we know in verification, because what we do in verification, there is specification, there is a program, and then we just have to check if the program adheres to the given specification. In this particular case, if you don't have spec, how you will know whether your configuration file is correct or not? So the other problem is like, okay, maybe let's then write specification manually. I mean, someone must have written all those configuration files. They must know what they had in mind. So doing it manually, first it's labor intensive, but the moment you start to do it manually, most likely you will end up with an error, right? So what our goal is to automatically derive specification about configuration files. And once we have this specification, then we will do standard verification techniques in the sense, now we will take new configuration files and check it whether it corresponds to the given specification. How we do that is the following. We take a large number of existing configuration files, then we learn the rules. Those rules are, for example, one library has to come before the other library, or some system variable has to be smaller than the other system variable. And then once we had those rules, when you give me a new configuration files, I'm checking whether it satisfies those rules. And if it doesn't, we can tell user, look, I think you might have error in your configuration. Maybe look out for this problem. So this is the big picture. Now to look it more into this big picture, you can see how our systems work. We start here from a large number of configuration files, and we translate them into some intermediate representation. We are doing this so that we are kind of almost like language agnostic. Whether your configuration files are for setting up Travis CI, or whether they're setting for MySQL, or whether they're setting for something else, we don't really care, as long as you have actually translated here from configuration files to this intermediate representation. Once we have this intermediate translation, then we learn those rules, and this will be template-based learning. So we will provide set of templates which we use to learn properties about configuration files. And once we have these rules, we just repeat the process that I have explained you. We check if the new configuration file that we are about to consider is to verify is actually respect the rules that we learn in this process here. If it does, we actually don't. We just say this configuration file looks fine. Otherwise, we report potential error. So now let's first go and look into translator. So if you look at translator, what we have here, when we look into configuration files, it is just a number of system variable or some sorts of environmental variables that we actually assign them some values. Like for example, in the MySQL context, we will assign max heap table size value to have 8 megabytes. Or when we talk here about some database, we will have general log file will be in the following log file, and this will be a Boolean telling us that we will have that. So how we translate that, we actually have a very simple translation. We just present this as an annotated tuple. So you can see we will put here the name of the environment variable, or which we call keywords, which will also have a part of its name to which module does it belong and what is its value. So this is a relatively simple presentation, and I'm also cheating a little bit because there is a couple of more parts in this tuple, but it's enough for presentations for presentation purpose. If you think which things are missing in the tuple, for example, in configuration files, you can also have guards which will tell you, well, if something is enabled, then do the following. If something is disabled, then the other, you set up the other values. So we will have also those guards and such simple tasks, but you know, like some simple details. But again, it's all fits into one single tuple. Now, the next thing is, now that we have our intermediate presentation, we want to learn the set of rules. And those rules actually are based on the, as I said, on the templates. And just to give you an idea how this rule, to remind you what kind of rules you want to learn, it's like what appears before, or we want to compare two system variables, which are talking, for example, about memory. Now, what we did here, we used something like called association rule learning. Initially, we were just trying to use neural network. We tried to be hip and cool, and we thought, okay, let's just kind of say we will train neural network on large number of configuration files, and when you give me a new one, we will just want to see if it's correct or not. And this actually didn't work well, because it's not only enough that we will say yes or no. We also need to provide to our user explanation. Why do we think that something is correct, or why do we think that something is wrong? So we can kind of rebrand ourselves like old-fashioned machine learning with explainability. So what we learned, which techniques would work the best for us, was something which was called association rule learning. That was a technique developed for in large databases, and they actually wanted to learn which tuples usually go together and which things that travel together. If you think about, this was used for early recommendation systems. For example, if you have bought bread and peanut butter, most likely you will also have in your shopping cart jelly. One example that they have seen in one of the slides for association rule learning is that if you buy beer, most likely you will also buy diapers, which I have to say came a little bit as a surprise to me, but let's now leave that on the side. That was association rule learning simplified for you. So what we wanted to learn was we wanted to learn a generalized association rule learning. What does it mean? Is like, again, using the same premises that we have two lists of the source and target words. Those are like things which we want to learn that they travel together. And then we want to learn in which predicates those words appear together. So for example, if you would have purchase together, then peanut butter and jelly would probably come together with the same predicate. And to put away shopping carts, what we are trying to do, and to go back to the configuration files, what we are trying to do is we want to learn predicates that are relevant for configuration files, namely that are relevant for this list of the templates that we have in our template database. So for example, when it comes to the libraries like MySQL and Recode, we know that they have to respect the ordering predicate, that Recode has to appear before. So this is the type of the property that we want to learn. If it comes to the two sizes of the memories, we want to learn that one always have to be smaller than the other. So that brings me, maybe I should actually tell a little bit more about this predicate database that we are considering. So looking at the predicate database, those are most of them. And you can see we will have ordering or keyword relation, which will just be a Boolean. We won't put any requirements on the type of neither ordering or keyword relation. Then we actually try to express that something will appear before the other that you have already seen. But very often another property is important, that if you have certain library or certain variable in the file, we will also need to have another variable as well. So then the other typical predicate is that we want to check type of something. So like, for example, will be X has type integer. If you remember our second example, there we learned that something has a type integer, and that we did complain, look, I know 100% sure that this has to be an integer. Then equality is when we have two things of the same type, then we can actually compare them. And then we also have more coarse grain and fine grain properties, which are defined either on integers or on the sizes. And this is where you can actually just compare them to see which one is smaller, which one is equal. Or we also have a fine grain. And I have to give you another example here that was very interesting, at least in our own opinion, of how configuration files, setting wrongly properties in configuration files can really mess up your system. So what was happening was someone complained, look, I set up things, just change a little bit my configuration file, and now nothing is working. My system, which is like super fast, super powerful, works incredibly slow for this particular program. And what has happened was, there was this variable somewhere in the beginning or the end, which is just allocating the memory for the system. And the system was actually spreading, using a couple of different threads. So you would have maximum number of threads is, let's say, 8. And then each thread had a buffer. So buffer of the thread would be, let's say, 50 or 100 megabytes. Now, if you would multiply number of threads with the number of threads with the size of the thread buffer, and if this would exceed the memory that you have, then what would happen is, like, within your own system, you actually had threads competing for resources. So you have denials of service attack without actually denial of service attacks, which is like, like, how would you detect this using standard techniques for software verification? You really needed to learn this, like from and analyzing other files, when you would conclude that multiplying those two values, like buffer size and number of the threads, has to exceed the memory that you originally allocated somewhere far away, maybe even, I don't know, 500 lines before or afterwards. So that's the type of the properties that we could infer from analyzing a number of the configuration files. So now you can actually maybe complain and say, like, let me show me those predicates again. And I'm showing you again. And you say, like, I can see now that you're talking about integer sizes and so on. And I could see how you would recognize that something is a size. Okay, you have maybe megabytes or gigabytes. But also, I could also just say total memory is 80. And maybe that wouldn't just tell me what is 80, but maybe there is some default before which says, like, if other not specified, it's megabytes. So now looking at that, then the question is, like, how can I now learn if something is a size or something is integer or something is Boolean? So could we just do syntactic matching? And we cannot. And to show you by just looking at, like, literally comparing strings and do syntactic matching, it won't work. What you can learn here, we have foo and bar, and we see foo is on, bar is 1. In the other file, foo is on and bar is on. So maybe by now you want to see, oh, foo or bar are always on. But then in the third file, we'll see that foo is off and bar is off. So you can actually say that what you thought that it's a good rule, it's not really a good rule. But what you can conclude is, like, oh, but I see that they're always equal. So I want to learn that foo and bar are equal. But can you do that? Not really, because, like, you can see that one is on and the other is 1. How you could actually learn that they are equal, because you don't have standard equality here. So to do this, we somehow make concept of typing a little bit more fluid, let's put it this way. The moment when you're parsing your files, what we then do, we actually collect all possible values of each variable. So if I would try to see what is foo and bar, I come in here, foo is on, so that's Boolean, bar is 1, so it's either integer or it's a size or it's a Boolean. Then I see foo is on and bar is on, okay, they're Booleans. Now again, on and off and off, I already know that those are Booleans. So, like, you go through every single file, and then you don't actually know what is the file of K, where K can be our either our foo or bar, but it won't be, it will actually just collect everything, like as you can see here. I will say it was integer so many times, it was Boolean so many times. If you have something else, you will just collect all possible files and have them in this, let's say, fluid version of the type. Once you are done parsing, then you will compare them to certain predicate. And if it satisfies, let's say, predicate given for integer, you will then conclude, okay, collapse everything away. And from now on, I know that K is just integer. If it satisfies predicate for Boolean, I know that it's a Boolean. And now that you actually derive what is the file of the each, what is the real type of the each variable, then you can actually apply the rules which actually say which things you can compare, which things you can derive more hard coarse grain or fine grain properties. Now to go back to example that I was telling you, let's assume that the predicate which checks if something is integer is just it appears more than 2 times, and if it's Boolean, it appears more than 2 times. So we collect our foo and bar and their fluid types, and after seeing which predicates do they satisfy, we actually conclude that this is actually what they are. Now, of course, in reality, this is not absolute. We just kind of this is not like here. It's more greater than 2 or it's greater than 5. It is relative. So if it's something was more than 90% Boolean, then we conclude it's a Boolean. So it's like predicates are a little bit more elaborate that you see here. This was just for demonstration purposes. Now comes the next step, which is now we have our types, we have our typed predicates, so we can clearly learn properties and how things are happening, right? So you have a couple of let's say you take a single configuration files. Now you will detect keywords, and then you will see what is their type, and then we'll just see which sorts of predicates do they match. If you can see that, let's say, I have some variable here that is smaller than some variable. Let's say variable A is 10, variable B is 20. In some other type, A will be 30 and the other one will be 50. So I won't really learn their relative values, but I will learn predicates that are satisfied as described before. So once we run through all these configuration files and we learn a bunch of the rules. So now let's assume that we learned, I don't know, foo was in most cases, in 50% of cases greater than A, and in 50% it was smaller than A. Can we call this a rule? Clearly we cannot, because there is not sufficient support for that. So what we have actually, to go back to configuration, to association rule learning, we have something which is called support and confidence. So support, here are the formulas, but let me not go to the formulas. Let me rather explain what do they mean. What does it mean? So support is like, how often have I actually seen this rule? Maybe, let's say, in one particular file, I learned that A is smaller than B. Now I ran through all other files and no one contradicted it. So I practically have a 100% confidence that this is a correct rule. A is smaller than B, except that it appears nowhere else in no other file. So can I actually now add this? In theory, it should be fine because it's a good, it's a good confidence. Nothing contradicts this from all the files that they went through. But what is bad is that if they haven't seen this rule often enough, that would be a pure source of false positive errors. Because now I have seen that A is smaller than B and I learn it as a rule. Nothing contradicts me. But it's seen only in one file. And now if a new file comes that actually claims opposite, that B is smaller than A, then I will report this as an error, just based on the fact that they have seen something once. So that's why we say it's not enough that you only tell me what is, it's only tell me whether the rule is correct or not, but you also need to tell me whether this rule is, appeared often enough. Now confidence would be a nice thing, would not even be needed if you would have perfect data set, right? If you would have a data set where everything is correct, then as soon as I learn one rule, but if something contradicts it, I could clash it and throw it away claiming, oh, this is not the rule. But that's not how things are, because if let me go back here, our configuration files, they're not perfect. So where we got those configuration files, I will show later the reference, they're actually coming from something which is called misconfiguration. So those are files which were once labeled as potentially wrong. So if I already know that I have a bunch of files which are labeled as potentially wrong, then maybe every single rule that I learned there doesn't really need to be true, because that may be one of those things that was wrong. So you can say, can we even then trust that configuration set? Yes, we can. I mean, and we cannot at the same time. Reason why we can is because it's a relatively large set. So having a large set means that not every single person will make error exactly the same on exactly the same spot. Maybe 5 of us make error there, but 20 others will make somewhere else. So when you have a large enough set, distributing errors through the set, it will kind of smoothen it out. So you maybe won't have 100%. If some rule appears in 90% of the cases, in 90% is correct, then you will say, this is pretty good indications. Probably this other part was when actually rule was flagged as wrong. So that's what we have is the rule that we have support and the confidence. And here is, again, simple example with foo and var, where we are trying to learn a rule whether they're actually equal. In the first case, we can see that they're already equal. In the second, they're not equal. And in the third case, the one doesn't even appear. So what we could learn rule that they're equal will be confidence will be only will be 50%. But we kind of give a pretty good support for that rule because the rule where foo and var can be both compared appear in the 2 of the 3 cases. So, there is some support and confidence is about a half 50-50. So now if you think about, can we accept this as a rule? Clearly not, because, it's 50-50, so it's either here or there. You can't really claim that this is rule. So I told you that I was talking that we have a sequence of this configuration file tools, and this properties threshold, this properties support and confidence are actually configurable. When you're learning all the rules, then once you derive the rule, you will check what is its support for that rule and what is the confidence. So here are approximately numbers that we consider. We will see more concrete numbers later on, but like if you would see rule sufficiently enough and it was pretty correct in the most of the cases that we could see, then we would accept that rule. Of course, if you want to again tune this, you could make confidence way higher or increase support, and you can make it much lower. So when I put what I put here is this config C was our initial version when we started to look in that problem. In that case, our confidence was pretty high, 100%. And the reason for that was because of the following. We had a really small configuration set to learn from. It was only 20 files, and we put human in the loop. Namely, we took our system person and asked him, go through all the files and make sure by hand that they're all correct. So, like doing this approach, everything that we learned was 100% correct because we knew that we started with correct set. And we really didn't need support because only one example was enough to learn because nothing got written, so this was a good example. Now you can see that this initial approach wouldn't really scale, so we had to kind of push human out of the loop and really then do as we do with a very large number, with learning from a very large number in the set and introducing support and confidence. Now, once we have our set of rules, which we did have, it was time to check our tool in practice. And of course, we sent this to the formal methods conference. So let me show you how initially we did evaluate. So I already told you that we have a data set that we use for, where we use for training. That was this data set published 5 years back at FSC. And in this particular case, I think we were here working mainly for this with Apache and MySQL. So what we did, we kind of filtered them out. There were 256 data configuration files, and then we would learn the rules. So we actually learned a bunch of rules. There was support and confidence that we actually derived, and for each of the rules. And then when we ran these rules on the around 1,000 configuration files, actually correctly, it's precisely 1,000 configuration files that we scraped from GitHub. We detected quite some number of errors, right? 62 for the ordering errors, 55 and 389 and so on. So now, of course, you may ask yourself, okay, you learned something, you detected an error, but did you really detected an error? So like, is this indeed an error, or this is just what you believe it's an error? So what we did first, we did some sanity check. Let's first see how the errors were distributed through the files. And it turns out in the most of the files were correct, which is nice. there were a couple of them, like around 200, which had one error, much less for them with the 2 errors. And you can see number of those with more than 2 errors is slightly decreasing. So that kind of looks to us like, okay, that kind of looks like a reasonable like reasonable distribution. But nevertheless, it really didn't answer, it was just sanity check. It didn't really answer our first questions. Are those really errors? So that's why we reach out to, again, humans, and we contacted our former colleagues that we knew that they're working on configuration files. One was at MongoDB, and the other one was at Microsoft. And we kind of randomly selected 25 files and asked them, look, can you maybe look into those configuration files and errors that we report? And could you tell us how many errors are there? And what would you classify as a false positive? So it turns out false positive rate was not even that bad. So MongoDB expert, who was actually working on distributed configuration files, he rated 13 out of 70 errors as false positive, and Microsoft person rated 8 out of 70. So when we look this and compare to existing tools like Encore, which is similar tool from now 6 years back, working on the similar projects and very similar approach, but without all these things with association rule learning. So we actually saw that false positive rate is somewhere around the same ballpark. So we thought, like, okay, now we have programs, we have real user data, sanity check passed. Human experts said, like, this is where you are, similar like the existing approaches. So let's actually see whether try to submit the paper. So we did submit the paper, and we got relatively positive reviews with an additional request. They say, like, well, you did scrape this data from GitHub, so why wouldn't you do now the following? Contact those people whose data you scraped and actually suggest them, ask them whether this was error or not. So now it's time, to feel like, oh my goodness, do we dare to do that? But we had to, so we did that. And out of this 1,000 people, majority didn't answer. Around 70 did answer. And positively enough, only one person, your client, was not really happy with our comments. Your client say, no, you cannot compare that. Jivin actually was exactly the person who said, oh yeah, thanks guys. No, this is very generic answer, right? It doesn't really mean that much. So I ask again my system people to look into this, whether this is a real error or a false positive, and because clearly your client was very angry about that, but it turns out it was really a real error. And it turns out, at least my system person claims it is a real error. Okay, but so that's it. But what was one thing that was very interesting and that we noticed from our users is the following. Many people said out of this that we contacted was like, well, thank you for reaching out. Yes, it is indeed error, but look what has happened. And if you would look a couple of instances later of my configuration files, you will notice that I actually realized that this was an error, and we actually changed this error. So clearly it was an error because I later on changed this, right? It was maybe not so unfriendly, but this is what people were pointing out, that they knew that this was an error and they did change it. So this was really good feedback, that we got from users. But then we did realize that what things that we were kind of missing all the time was that we didn't look into this temporal problem of errors, right? Especially if you think like GitHub and other repositories, we could really look into configuration files, see how they're changing, see how they go from erroring state to the correct state. And actually, based on this, we could kind of learn maybe new, more and complex properties. And this was exactly the problem that someone at CAF conference, when we first published this work, they asked us like, hey guys, could you do this on Travis CI configuration files? And the reason is this person said like, look, I'm managing the small team, and very often, when we commit, I'm seeing them waiting just for build to complete, and yet, afterwards, then build fails, and then we have to go and try to figure out what is an error in configuration files and scream on the person who was the last one to change configuration files. So that's why we realized, okay, now let's look into this thing. That was this temporal aspect was there that we kind of realized from the users, from a given aspect for the user given from our evaluation. But now it's also a demand from a person in industry who asks us, could you do that? And I don't want to spend our time on introducing you to configure to continuous integration and Travis CI. If you don't use it by now, you should. I mean, it's a very widely accepted programming environment and methodology. But what when you're building your configuration files in Travis CI, if you think about that's again configuration files. And yet, when you look at the big picture, this is where the problem can happen, right? If you don't manage to build, I'm not even going here into your test suite because maybe you wrote bad code, maybe you wrote bad tests, but I'm looking at the step that happens before. If you're here, if you don't manage to build, then you're all the parts that happen here won't really happen, will not really happen at all. And I think, I think a couple of weeks or months back, we did simple script where we were running on GitHub just to figuring out how many times people spent on waiting for build to finish and actually for build to when build would crash. And it turns out it was something really scary, like 77 years or something around this. I mean, all across GitHub, but think about that's a really large number. So now let me show you a typical case what happens. And I mean, if you look at here, you can see that on the February 4, everything was, you can look at this small error, everything was fine, build succeed. And then someone changed something and things were just going bad. And only later on February 27, which is more than 2 weeks later, things managed again turned from bad to green. Now, I assume it's not that people were just changing their configuration file, but what I believe was that, what I believe this was just, something someone should fix it. But, like people did try to fix it. But, if you think everything that was coming afterwards, like, can you commit, can you build, can you integrate? This was not, people could not really do that. So now let's look, if you look closer to these logins, logs, what was happening was you can really see that build has stopped, and similar. So to show you what are we trying to do now is we kind of try to again apply all these techniques that we have learned about configuration files and their verification and checking for potential error and apply them here. We actually want to report if there is a potential fail if your build will potentially, if you change configuration file and there is a chance that the build will fail, we want to report that to you. And not only that, we also want to point out what is the error. So playing the same technique, only a different problem, because now we also have this temporal component. We know what was happened before and we want to learn from that. So again, if you would look in this particular example and we would run already on the first failed build, our tool called VeriCI, it will tell you, okay, I see that you have error in the file 7, blah, blah, something, and something about encoding. Maybe we could have nicer error, but anyway, error is clearly pointed out. And now, if you would look at what has happened on February 27, is exactly, that was the error that we pointed out and tell, look, this is a problem. That's what the user given here fixed, and then actually we knew that our tool detected the right error. So you could ask yourself, this is pretty interesting, but didn't people already address this? Yes, they did. They did. Actually, there was a whole workshop at ICSI a couple of years back, and it was really interesting because people would use all sorts of metadata. For example, they would look how many emojis that you use, how many numbers of lines that you use, how many lines of code you change. And believe it or not, this is really high accuracy, right? It's not really that you say, oh, based on your emojis, I believe you will fail, your commit will fail. But then again, reason why this is not so surprising is because, machine learning works in practice, right? But for us as a formal methods person, we cannot really we could not really say, okay, this problem is addressed, because like if I'm running this and I don't want to just see someone, hey, you didn't use enough emojis, so your thing will fail. Really point me onto the line while it will fail and tell me what is the reason why we think it will fail. So this is what was our big goal. And technical challenges to address this were exactly the same that you have seen before, only much more complicated, right? I don't need to tell you there is no specification and there is semantics are complex and so on. But what is now in addition is like, we are now talking about several projects, right? There is this temporal aspect. There can be many languages, can run on many new environments. So, like now there is this addition, there are several additional components. So let me show you, because we are running out of the time slowly, let me just give you some flavor of our tool called VeriCI. So what we do here, we have all the past commits, which will now be our training data, right? So we take all the repositories that had happened before, and I give you this, and then when you do new commit, I can actually then run our tool. And if I think that if our tool thinks that you will pass, we are good. You don't do anything. We just tell you thumbs up, you will do fine. But if it turns out that we think that we think that you will fail, and we look at the error. So like one thing that was very big problem to us in the beginning was false positives, right? So you don't want to just report a message when you say like, oh, you will fail because of X. Like that's not enough. You need to give really strong and confident and clear message why you think the things will fail. And then if you have a high confidence that the message that you get here is correct, then you will report it. Oh, I think you will fail because of the following. And if you have very low confidence, then you just kind of ignore that. And like maybe it's much less damage if you don't report error than if you will report a wrong error. So now let's maybe look into those circle things. There are many other aspects that I could talk on about, but let's just maybe focus this abstraction-based labeling and how do we do message filtering. So the goal is not only that we don't want to do that, we cannot incorrectly predict errors, and we cannot also incorrectly localize errors. So we really need to be to the point and precise. So let me now tell you, since clearly I'm talking about machine learning and stuff, clearly I need to have some feature vectors. So what we will do, we will use some so-called magic constants. So tell you about the magic constant, they're just constants. So you parse through your configuration files, and whenever you see a constant, you actually export this again as a tuple. This time we call it feature vector. So each file will be one feature vector. Now, you can ask, is this enough? In principle, it is, because we actually try to introduce a couple of more abstractions, but even with this only a single abstraction, we are in the ballpark around 90% accuracy. Adding more abstraction increases only, I think, for 1% or 2%, but nevertheless, it added in incredible computational overhead, because you just need to recompute and repeat everything. So at the end, we somehow just concluded it's, like looking at computational power, going suddenly from a couple of hours to more than a day, it wasn't really worth. So we right now are working on with one single abstraction, and this is this magic constants. Now, once you know what is our abstraction, let me explain you briefly what is abstraction-based labeling. You can have many repositories, right? Let's currently focus many to before. And if you look at their original status, the first one managed to pass, so it's successfully built. I'm not talking about test, I'm just talking about build. The second ended up in the error, the third one passed, and the fourth one also ended up in the error. Now let's look R hat, which is a feature vector of this repository. It is 1010. This is 2020, no, 2010, 2010. So looking from perspective of abstraction, those two repositories are exactly the same. And nevertheless, one is passing and the other one is erroring. So the repository 2 didn't manage to build. Now, if you think about it, why is this the case? Well, clearly there is a problem that is maybe either we don't have strong enough abstraction, and unless this is I'm not going into this, but there are also many other cases that are even outside of our reach, like for example, network failures, hardware failures, and similar techniques, similar problems. In that case, we can really not capture that, right? So, fact that R2 didn't manage to build, maybe it's really just there was some glitch in the network. So what we then do, all the erroring stakes and repositories which have the same abstraction values as a passing repository, they are relabeled, because there we can't really learn anything about erroring. So that is abstraction based relabeling. And reason is for this is because we don't actually try to predict errors from something that we would get contradicting comments like. So now let me go back to the next thing is like, what do we also need to do is very shortly, what is something called what do we do about message filtering using neural networks? So we actually just use scikit-learn library, and what we do is the following. So we use something called cascading decision tree. That's also what we introduced. And if you think about decision tree is something that is takes a feature vector and then just goes through all various questions and then tries to classify it at the end of the day, say like, look, you guys, you belong to this class, or you belong to this class. So on the leaves, you actually decide whether your input is type something of X or something of Y, and so on. Now, let me assume that I have a repository and I'm asking, okay, are you using this library? Yes, I am. Are you using the following library? Is your library greater than 7? Is it smaller than 5? So based on all this relabeling, I'll say, okay, I predict now that you will fail. Now I have a very long path, and if I want to report to the user that you will fail, I will tell, because X was greater than 7 and you use library smaller than 5, and so on and so on, I think you will fail. Now, if you give this all to the user actually cannot learn much. It will be really long messages like, oh, let me just see whether I will fail. What you want is something very succinct, and this is what are our cascading decision trees, which says like, okay, let me really isolate which is the source, which is the main root cause for these things to fail. And this way you're actually getting, instead of having very large trees, you will get messages in the in a practice in 1 or 2 main root causes of the failing we would identify and parse to the user. Now, fact is, this is again prediction based, so we might actually guess something totally wrong, right? So what we do when our cascading decision tree gives us an error, we actually look in the past. And from the past commits here, we see whether there was a similar message error and whether this message error was when later on it was causing things to fail. And then whether when it was corrected, whether it was indeed because of the reason which our error messages is pointing out, which you just do using diff, right? And once we see that if this is indeed the case, then we kind of consider this error message as a high confidence that this is an error message. So if you think about the great scheme, how we envision using this tool would be as follows. You run your tool every single day. At the end of the day, you run the learning process to kind of see what was problem this day, to get more accurate messages, and do this classification and repeat this every day or whatever is your time schedule when you want to do a relearning. So we did evaluated this problem on the real world data. By real world data means we were running some data found on GitHub, not by some big company, but publicly available data. And when we would switch on both cascading decision trees and abstraction-based relabeling, we would get accuracy which was close to 91%. So, when I will tell you whether your things will fail, I can immediately tell pretty accurately. I can, say, well, 91% I would be right. And if you think why we could check easily accuracy, because we would take repository, train up to a certain point of time, and then we would check just for next commits. So when we would see that you change your configuration files, and we would tend to predict whether it will fail or not, and then we would actually be able to see how accurate we were. And it was almost with 91%. And also, if you look at what was our average depth of explanation, was practically 1 or 2 or sometimes even 3 messages. I say, like, I think you will fail because of the following and the following. Sometimes maybe only one thing would be the error. So user could immediately have incentive to look into the problem that is pointed out. It means, like how accurate were actually our messages that we would find. And then you can see that both cascading trees and abstraction-based labeling are relevant. So to conclude, I hope that I showed you that configuration files are really interesting, and there are many important new problems. If I would have more time, I could tell you more about our projects. It's like one is about silent configuration errors, which are indeed those configuration errors that you cannot see, but they're still there. So then they're unfortunately often overlooked by program analysis community, but I think that this work can show you that nevertheless you can approach this problem with relative rigor of that formal methods do require. Then usually people complain this, people say, like, where is this a system? No, I'm really thinking about this, that this is more like software synthesis, because if you think about program synthesis is not about synthesizing some smalls of programs. Here we are synthesizing specification using various learning techniques, and then using this specification, we are verifying configuration files. Of course, large data corpus was needed to do that, but it worked nice for us, and results are promising. So all the tools that are there are publicly available and tested on real-world data. And if you have any questions, which I hope you have, I'm really ready to take them now. I would also like to thank all my amazing collaborators before that. Mark Santolusito, who was driving force, my former PhD student, and currently a young professor at Barnard College, my former postdoc, Enan Jai, and also my current student, Zhang, who actually took this project, and all undergraduates who were involved also in working this project. So thanks to them, and thank you all for listening. I'm really happy to take your questions now. Thank you.